Howdy! In this video we are going to go over greedy algorithms. Alright, so what is a greedy algorithm? A greedy algorithm is basically a simple intuitive algorithm that is used in optimization problems. So basically what a greedy algorithm does is it tries to make the most optimal choice at every step in the while solving the problem, and then the most optimal choice eventually ends up being the best overall choice for solving the problem. Some examples of greedy algorithms include Huffman encoding, Dijkstra's algorithm, Kruskal's algorithm, and Prim's algorithm. Alright, so let us look at one of the examples of using greedy algorithms. So the single source shortest path problem is a very famous problem within computer science. So basically what we're trying to do is um, we're trying to find the shortest path from a particular vertex v. In this case, for example, we're taking the vertex a as the source node, and then we're trying to find the shortest path from a to b, a to c, a to d, a to e, and so on. And so basically the general method to solve the single source shortest path problem is known as the Dijkstra's algorithm. Now this Dijkstra's algorithm is a very good example of greedy algorithms. Dijkstra's algorithm finds the path with the minimum cost from one vertex to the others in a graph, and then it keeps doing that until it reaches the end. And so that's why it's basically called a greedy algorithm, because it tries to make the most optimal choice at this step, and then it will try to keep doing that. Okay, let us look at one more example of greedy algorithm in detail. So one another example of greedy algorithms is the Huffman code or Huffman tree. So Huffman coding is basically an efficient method of compressing data without losing information. So basically what the Huffman algorithm does is that it analyzes a message, and depending on the frequencies of the characters used in the message, it will basically assign a variable length encoding for each symbol. The problem with ASCII codes was that we're using the same length of encoding for every symbol, but then that makes it worse compared to Huffman coding. So in general, Huffman coding is considered to be a more efficient way of compressing data without losing any information. And so the idea over here is that the more commonly used symbols will have a shorter encoding, while a rarely used symbol would have a longer encoding, and thereby compressing the data. Okay, so here's a quick example of Huffman encoding. So let us assume that we have a sentence or like a file or like a string which consists of 5 characters, which are D, E, V, R, A. These are just randomly picked, and then they have random frequencies. So for example, in that particular file or in that particular string, the character D has a frequency of 6, and then E has a frequency of 15, and so on. And so basically the way we use Huffman encoding is that we'll try to make a node for every character and have a value for each of these nodes. So for example, D has value 6 because the frequency of D is 6, then E has value 15 because its frequency is 15, and then so on. And then we'll first try to basically sort them. So note that the order of these nodes is now sorted. So it's 4, 6, 8, 15, 18. We sorted it in ascending order. And now we'll pick the two smallest nodes. So in this case R and D, and make a node, a parent node for R and D. So we now have a single node which basically represents R and D. And we'll again try to sort these nodes now. So this new node becomes 10, and then there's 8, 15, and 18. So when we sort it, we get the new node basically is second in line now. And then we again do the same thing. We pick the two shortest or like the least occurring nodes, which in this case is 8 and 10, and now we'll make a node in between them. So we get a new node which has frequency of 18, and it has the left child is basically 8 and the right child is 10. And now we'll again sort these nodes. So we'll sort 18, 15 and 18. So we get 33. Oops, there is a missing slide over here, but basically we try to sort these three nodes. So we'll get 15 and then 18 and then the other 18, and then the lowest nodes or the least occurring nodes basically are the first and the second one, and so we connect them with a root node, and so we get a node which is 33, and another node which is basically 18. The new node basically has E, which has value 15 as its left child, and the new node we made using V and the combination of R and D as the right child. And then we sort it, and then again we'll create a new node, and so that's basically how we'll do Huffman encoding. And now we'll give values to each of these edges. So we give value 0 to the left edge and 1 to the right edge. So we get 0 over here, 1, and then 0, 1, 0 over here, 1, 0 and 1. And based on this, now we can encode these characters. And so the way we encode them is we basically say that the character D can be encoded as 1111, and the way I get this is D is over here, and so I start from the root node and then I go right, so I get 1, then another right, right and right, and so that gives me 1111. For E I have an encoding of 10, which is right and then left. For V I do right, right, left, so 110. For R it is right, 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 left, so 1110. And for A it is just 0. And so basically that's how we get the encoding for each of these characters. Okay, so let us look at an algorithm for Huffman encoding using binary tree. So basically what we do is we have a for loop running from 1 to n minus 1. Over here n is the number of unique characters, so in this case it would be 5, and then we basically allocate a binary tree T with single node Z, and then we insert T into the priority queue. So Q is basically the priority queue over here, and then we say that left Z, so Q is basically a minimum priority queue. It basically sorts the nodes from the minimum value to the maximum value. And so when we extract minimum, we get the left node for this binary tree, and we again extract minimum from the queue, and so we get the right node, and then we'll basically try to add these two nodes to the binary tree, so X becomes the left node and Y becomes the right node, and so we get that, and then we insert this new tree or the new node into the priority queue, and then we keep doing that until we get this complete tree, and basically after that we'll return the extract minimum queue, and that will basically give us the Huffman encoding. Alright, so let us look into the runtime for these algorithm. Okay, let us assume m is the length of the file or the string from which we are basically taking this. So in this case the length of the file would basically be the sum of all of these frequencies, and so that would be something like 6 plus 15 plus 8 plus 4 plus 18, which should give you around 51. And then the cost of creating the table, so the cost of creating this table, the frequency table without the encoding part, would be big O of m, because you basically iterate, or like you basically have to read every character in the file or the string, and then based on that you have to update the frequencies of every character, and that's how you get the cost of creating a table to be big O of m, and then the cost of creating a minimum priority queue, which in this case was the priority queue q, is oops is big O of n, where n is the number of distinct characters in the text file, and then the extraction of the first and the second minimum from the heap and insertion of the node into the heap takes log base 2 of n time, and then this step is basically repeated n minus 1 times because there's a for loop which runs n minus 1 times, and that's basically how we get a total of big O of n log n operations for this particular step of extraction and insertion of nodes, and that basically gives us the total running time of big O of m plus n log n, where m came from here, this step of creating the table, and n log n comes from the insertion and removal or extraction of the minimum nodes. And after we encode this, now we also need to decode this, right? So for example, if you have an encoding of, or basically if you have a Huffman encoding, the way we decode this is basically we start from the root, and then if the encoding has a binary value equal to 0, we go to the left subtree, otherwise we go to the right subtree, and whenever we go to, or like the left subtree, we'll basically have a node, or we could also have a, basically whenever we end at a leaf node, which means we can't go to there, which means a node which basically doesn't have a child. So in this case, A, E, V, R, and T don't have children, which is basically a leaf node. And so at these nodes, we basically extract the character, and then we try repeating the step 1. So we go back to root, and then we again basically encode it, or sorry, decode it. Okay, so now let us understand how this is helpful to us in like encoding and decoding it. Basically, we are trying to minimize the code length of the text. So if we have a particular file or a string, we want to encode it in the minimum number of characters, so that in that way, if a particular file can be encoded in like 10 characters, then it's easier to send it to something else. So that's basically a way of data compression. In this example, if we have the way we find the code length of the text, the average code length of the text is that we first find the total number of characters, which is the sum of all frequencies. So I added 6 plus 15 plus 8 plus 4 plus 18, and I get 51. And then I find the product of the length of the character and the frequency of the character. So 6 multiplied by 4, because the length of the code of D is basically 4, so that's how I get 24. And then 15 multiplied by 2, because the length of this is 2, and so that's how I get 30. And then 8 multiplied by 3, 4 multiplied by 4, and 18 multiplied by 1. And then in step 3, I'll basically find the sum of the products I found in step 2. So I'll find the product, I'll find the sum of all of these products, which gives me 112. And so the expected code length is basically, the expected average code length is basically 112 divided by 51, which I get from dividing 51 from 112. And so, okay, so we understood what greedy algorithms are, but let us try to understand which algorithms are basically not greedy. So some examples of not greedy algorithms are Bellman-Ford algorithm and topological sort. The reason for this is that we basically don't make greedy choices or like the optimal choices at every step. We're trying to think of like the big picture in these algorithms, and that's basically why we're not making greedy choices. And so sometimes it's more important to not make the greedy choices so that we could like focus on the bigger picture. And so these are some examples of algorithms which are not greedy. And so yeah, I guess that's about it for greedy algorithms. Thank you for watching.